Hello, everybody. My name is Cormac Purcell, and I'm here with Anshel Bassi, and we will be your hosts for the 2022 Europe Live Showcase. A really warm welcome to everybody joining us. We're super excited to have you here. The two teams will present their results in just a little while, and we'll follow up with a panel session on Earth system digital twins for disaster response. But first, we'll kick off with a retrospective look at 5 years of FDL and a little glimpse of what the teams have been experiencing over the last few weeks, indeed built upon months and months of work to get us into this place. But first, I'd like to thank our partners, without whom supported by ESA, Google Cloud, NVIDIA, ScanAI, Planet, Deorbit, Sense, Pasteur SI, Airbus, Catapult, and last but not least, the University of Oxford. Thank you so much. You have been great supporters of us through 5 years of FDL. I'd especially like to give a warm welcome to our NVIDIA and SCAN partners who have been our compute partner for this year's Frontier Development Lab and have really gone above and beyond to support each of the teams in the work that they're doing. And much of the work is built on the foundation of the scale that they bring to the compute. Google Cloud has also been a wonderful partner for all of FDL, both here and in the US. And it's on the Google Cloud backbone that we are able to scale and build much of our machine learning research. Okay, so we've come a very long way in the last 5 years. FDL Europe started in 2018 and started out already with the theme of responding to disasters when the teams were looking at mapping flooded and collapsed building from remote sensing data and also looking at informal settlements, all using open data from the European Space Agency. Moving into 2019, we got even more serious and about our machine learning, and one fantastic result from that year was the Cumulo dataset and the first global cloud classifier. And so this was a dataset of clouds for the entire planet over the course of a single year at kilometer resolution. And it won Best Paper at the NeurIPS Climate Change Workshop. One of our most enduring Frontier Development Lab results also started this year, and this was our world floods results. This was an effort to build a flood mapping system that could be compressed and put onto a satellite. And the initial result of this made it into Nature scientific reports. Indeed, in 2001, it was the first FDL result to make it into space, where we proved that we could use this result in order to rapidly map floods and also to rapidly adjust the machine learning algorithms for new cameras. And it's being developed even further still to map floods around the planet now. That year also saw us look at space situational awareness, in particular, satellite constellation path management, which is a very difficult task, trying to figure out when to upload or download data from satellites to a limited number of ground stations. And this result has been, or aspects of this result have been taken forward by the European Space Agency into deployment. Moving on again to 2020, this was when we first started looking at our Earth system digital twin and built our very first whole Earth digital twin. So PyRain was an effort to do global precipitation forecasts over the whole world using a neural network approach and could get to results in just a few minutes, predicting rain at kilometer scales. We also looked at causal evolution of marine clouds. So looking at how the clouds would be tracked and evolved, and how aerosols would affect whether they evolved into one cloud or another, and to understand the factors that led to the evolution. And then finally, in 2020, we looked at spacecraft collisions and using a Bayesian inference machine learning approach in order to predict the dangers of collisions between multiple spacecraft. And this is a result that's also being looked at as potential for deployment. Last year, we continued our work on machine learning on board we built a variational autoencoder-based change detection system. And this was something that was trained on our flooding data, but it was applicable across the board to multiple different types of disasters. And some of the smaller images that you can see here is looking at burn scars in the landscape after a large fire has swept through, but it also works for hurricanes and damage of buildings and land. The same year saw us looking at supervised self-learning for agriculture. So it's a big problem if you have a lot of data, but not many labels. How do you propagate those labels out in order to figure out what crops are grown? And so our World Foods system allowed uncalibrated sentinel data to be labeled in order to work out harvest yields. And then finally, a little side project was very successful, taking 10-meter sentinel data and using multi-image super resolution in order to get down to 4 meters. And this is, could be applied all the way across the archive of sentinel data in order to really get fine-grained details from lower resolution images. And then I'm very pleased to move on into 2022 when we introduced our latest aerosols and hydrological twin teams who have been working over the past 8 weeks very, very hard, but built upon months and months of support work and preparation. These are our teams, and this is the FDL Europe support team at the bottom. They will be introduced in their own time. I'd like to hand over to Anshal, who's going to just give you a little bit of a taste for what our teams got up to over the last part of the sprint. Anshal,
awesome.
over to you.
Thank you, Cormac. So as Cormac said, we've had an incredible past 5 years with FDL. And sometimes when you think about FDL as a program, you think of it as a summer sprint. And what people don't realize is to get to this summary screen that you're looking at here, it's a year's worth of work. It's a lot of effort in the background and a lot of magic that happens to make this moment possible. But in true sense of achievement and drive, FDL kicks off with the boot camp, which is the beginning of our 8-week sprint, which is part of our entire research program. This sprint was inspired by ESA, who said that we needed to have a pulse on our planet. It was then further motivated by Chris Rapley, who said that there is a code red for humanity, and by Simon Reed, who said we actually need to think about infrastructure for space. Alison Lowndes came in to inspire us and talk to us about digital twin and how our entire landscape is changing and how machine learning and AI are going to become part and parcel of our lives. And with this, our teams were empowered and inspired to go forth in their research adventures. And adventures they were. There were definitely times when they were challenged. There were definitely times over the course of 8 weeks where they have had input and have had to tack, if you were to think of a sailing term, and completely change course on what they needed to do. But the teams have thrived. The teams have come together as one. And I think this is a moment to just take a second to appreciate the fact that these researchers, mentors, faculty, everybody's come together over the past 8 weeks, but also over the course of last year, and have not necessarily met in person even once. And I think that's an incredible feat to achieve. And we should definitely be thinking of that when we think of the results and listen to what these teams have to say. Because if you're not in the same room as someone and can achieve this, imagine what we can do when we can get together. With that, I would like to hand back over to Cormac, who is going to introduce you to our panel.
Thank you, Anshal. That's a lovely glimpse at the experience of our FDL researchers and faculty. So we have some special guests who are joining us. We're joined by representatives of the European Space Agency, experts in Earth observation and suppliers of much of the data that have come into this. into this challenges instead of challenges. We're also joined by folk from NVIDIA and SCAN, who have amassed a huge amount of expertise in building digital twins and supporting very large science and computing workflows. We're joined by Google, who have done the same, but also who have their own hydrological team and can offer some great insights to us there. And then also by natural catastrophe specialists and climate change specialists who will give a unique insight onto how the team's results may be able to be used. And we will hear from all of those in the panel afterwards. But before I hand over to the teams, I'd like to just hear from a couple of our specialists and just wonder what their expectations will be for the next hour. Okay, so Pierre-Philippe, can I ask you, what's exciting about emerging ML when it's applied to Earth observation data?
Okay, hello, Cormac. Can I just check you can hear me?
Yes, we can hear you.
Okay. Then you will have to repeat the question.
No problem. I'm just wondering what's exciting about emerging machine learning when applied to Earth observation data?
Okay, it's in fact extremely exciting because the outfit I'm working it in, which is called the FDL, is now focusing most of his efforts of trying to transfer the capability of machine learning, often developed outside the field of space, and to transfer this capability to geospatial data.
Mm-hmm.
And what we notice is that it's really a revolution there because it's a totally different paradigm, as you know, as opposed to coding, we are learning from data. And because we're in the business of big data, this is very exciting. We really want to learn the representation of this Earth observation data. We want to have a kind of tensor view on what the data tell us about the planet so that we can really and fastly check what is changing on the planet, if it's relevant in context, and then provide this information to decision maker. What we have noticed is that our community started to jump on this, let's say in the last 5 years, significantly with the increase of number of papers. And in the last Living Planet Symposium, which is the major event of ESA and Earth observation in Europe, I was strolling down the corridor of posters, and like 4 out of 5 posters were using machine learning. So this is really a tool which is becoming mainstream, but there is still a very strong innovative part at it, because people are using convolutional network in computer vision these days by transferring open software from the web. But there is this whole business of simulation, of emulation of model, of generative models, of reinforcement learning, all these new learning paradigms that are popping up every week that we are really excited about, that can really transform the way we do Earth observation. So this is why FDL plays a key role in this, because over the last few years since we started, I have seen a very strong and consistent approach to untap this potential of machine learning, because as you know, it's very easy to build correlation. It's very challenging to understand if it makes sense. But the team were really strong in this physics based approach to machine learning. And so my expectation is very high, I'm afraid. So also you built up my expectation by telling me I should be waiting for amazing results.
That might have been my fault, Pierre-Philippe, sorry.
Okay. Anyway, I will adjust in real time, but this means this is a very hot topic, this digital twin, because we realize that one of the major impact of this technology is really to work in a hybrid way with models, possibly complementing some part of the prediction chain, in particular in weather forecast. We see this very strongly because machine learning is fast, it's scalable, it works on different machines. each time there is more data, you improve. So I can see this trend coming very strongly, and digital twin based on machine learning is certainly a key component of what we will be doing in the future, especially that it's data driven. So it comes also from the Earth observation part, not only the modeling part. So all this to tell you that you are working on something that is likely to make a huge impact on the way we process data, but also on the way we make mission. And you have already demonstrated it by bringing the software in space, showing that the brain can be orbiting and can be reprogrammable, etc. And I'll stop there with a high expectation. Thank you.
Excellent. Thank you, Pierre-Philippe. I might go to Sumik next. So Sumik, can you tell us how you and SCAN have been supporting the teams over the last 8 weeks of research and beyond?
Thanks, Cormac. Yeah, it's been an absolute honor and pleasure to work with these teams and just watch them go from defining a problem and an idea and take it to the digital twins level. So from SCAN, we set up the entire Omniverse and digital twins environment within which they were, at least the teams who went to that part were able to develop the digital twins, and also we provided the DGX environment for doing the machine learning and training their models. The teams just they were at it, and they did a fantastic job in the limited time given, and I think they were able to use the resources given to them as much as they could.
Fantastic. Yeah, it's really good to see that they were able to scale to use the resources. Alison, have you managed to get on? I know you were having some technical issues before.
Hopefully you can hear me, but for some reason I can't get my video to turn on.
We can hear you.
With this platform.
Yes, we can hear you, certainly, yeah. Okay, great, Alison. Welcome. And so I wanted to know what was NVIDIA's interest in supporting Earth system predictability?
So I've been with NVIDIA for over 7 years now, unbelievably. And since day one, I've been pushing for us to be doing much more on space, because I've got an astrophysics background and I'm just a complete space geek. So, you know, when I met James back in 2015, it was like, oh, you know, perfect. Let's get going. The trouble with space is revenue. So what we have to do with all of the technology that we develop and that is constantly evolving is concentrate on the Earth focused. So, you know, if you take a digital twin, for example, we have to focus on self-driving cars, we have to focus on factories, we have, you know, really Earth-based. But at the same time, that same physics, that same mathematics works for space, whether it's for a spacecraft, whether it's for you know, 5G networks around the moon and beam propagation. It's all the same. So I have to work within the limitations that I have of, you know, of a small team, but prepare for the fact that the you know, our spacefaring nation is becoming what it is. So I'm the one who's constantly drumbeating space and prepping everyone, but also pulling in everything that we do at NVIDIA and focusing, you know, that directly at the space ecosystem, and that's huge. And fortunately, or let's say unfortunately, with the situation with climate right now, Earth observation and satellites are really front and center. You know, my friend runs a luxury campsite in Toulouse, and it's been 40 C there for almost 2 months. You know, the only way you can cool down, and you can cool down his dogs and animals, is with a hose pipe. But now the area's run out of water, and all of this, we know about this. You know, there's problems with Europe's rivers, and you know, 80 billion euros is normally transported down there. But to be honest, the saddest thing that I've read recently was a politician saying in the newspapers how they hoped that this would be an exception. It simply isn't. You know, this is the future, and we have to prepare for it. And that has actually pulled in the focus for space and Earth observation and everything that we do around satellites and bringing that technology in. So, that's what I'm, I hate to say excited to be helping with, but certainly mitigating and helping climate adaptation strategies.
Yeah, certainly the maxim, what isn't measured isn't done, applies here, and that seems to be what NVIDIA is supporting, the ability to measure and predict. It just so happens that space is the right field to be in at the moment. I'd like to go over to Zahan. So Zahan, why is disaster response also important to Google Cloud? And maybe I'm going to ask a second question on top of that as well. Is where do you think these sorts of efforts are going to be in the next 5 to 10 years?
Sure. So thank you so much, Cormac and James, for including me in this event. I think before I answer your questions, I should probably just qualify who I am and what I'm qualified to speak about. So I'm very new to the work of the FDL. I only connected with James earlier this year. I've been at Google for a long time. It'll be my 14-year anniversary this October. My day job, based in our London office, is more focused on the business and marketing side of our operations. So I'm not part of Google Cloud, and I'm certainly not an expert on AI or ML or the technologies being discussed here today. That said, over my time at Google, a large part of my job has been helping various teams respond to crises and disasters we've seen around the world, whether they be acts of terror or humanitarian crises or natural disasters. And when I look back at all these experiences, there's one thing we've learned is that information is oxygen. The more you can provide reliable or authoritative information to help people during those moments, whether there are people directly affected or people around the world wanting to know what's going on, information is oxygen. And in fact, about 6 years ago, I was part of a very small team at Google, led in fact by engineers based in our Israel office, to develop a new set of features across our search and maps product called SOS Alerts, which were essentially designed to make it easier for people to find that authoritative, reliable information to help them take the necessary action to stay safe. And so that was like 5-6 years ago. But then when I think about what's next for products like, or features like SOS Alerts, it's about not just the information you can provide during and in the immediate aftermath of a crisis. It's about predicting crises and disasters. And so take floods as an example. Thousands of casualties every year, billions of economic impact. One of the most devastating natural disasters, and the single best way to stay safe is to be able to evacuate in time. And this requires the ability to predict. And I think if I were to speak to some of the teams 5-6 years ago at Google, they weren't entirely sure whether this was a solvable problem. But since then, with the use of satellite imagery, detailed models of land and rivers, combined with AI, combined with cloud technology, working in partnership with governments and local authorities and other partners, we have been able to develop prediction algorithms. And I found out that in the last monsoon season in India and Bangladesh, we were able to send out 115 million notifications to people at risk, alerting them about floods with over 8 hours notice, and able to predict water depth with a 10 centimeter error margin. So again, like a few years ago, I certainly would not have thought that was possible. So I'm very, very excited about what the next 5-6 years can bring in terms of the potential of these technologies and that combination I described to further help people affected by this.
Fantastic. Well, I hope you like what our teams have cooked up now and how it adds to that vision also. Okay, I think we'll end the discussion there until we get to the result, to the after panel. So it is my great pleasure to introduce the hydrological team, who will be presenting first. Thank you.
we've seen a lot of news recently that suggests that the hydrological cycle is completely in overdrive, with droughts and floods happening everywhere, with little to no warning, and really spreading across spatial and temporal scales that we've not seen and experienced before. Therefore, the hydrological community in recent years have looked into creating regional and global harmonized databases of important parameters to help improve prediction capabilities. And machine learning is just one of the tools that could be game-changing. But so far, what the community has done is looked at rather simple models or even LSTM-based models, but those are not the right tools for explicit representation of uncertainty in hydrological prediction, which is actually what is needed to make better warning systems. So here I would really like to thank our partners, subject matter experts, faculty, and of course the amazing research team for helping pave this way.
Good morning, everyone. I'm Omer, and I would like to welcome you to our final presentation of river flood predictions. We are the hydrological models team, and let me first introduce you to our team members. At the top, you could see the researchers: Mano, Mr. Robot, myself, Mr. Time Series, Joanna, Miss Astro, and Kike, Mr. Sentinel. And at the bottom, you could see our team leads: Dietmar, Mr. Geoinformation, Guy, Mr. Flood, and Piotr, Mr. ML. So let's start with some footage. You could see here a river flood in Kohistan, Pakistan, approximately 2 weeks ago. This is a devastating river flood, and our project is aimed to help emergency agencies prepare better for such floods like you have seen here. This specific flood has left hundreds of people homeless, without access to food, and without clean water to drink. And you might want to calm yourself down and say, this would not happen to me, to you, to us, but this is happening all over the world. So in this video, you could see the red spots over the world map. These red spots coming up on your screen are river floods happening everywhere. And these are becoming more intense and more frequent in many areas of the world due to climate change. And for this reason, it is time for us to act now. So why now? Well, there is the urgency, as I just mentioned, from the exacerbation of severity of events due to climate change. But there's also a new opportunity now. The opportunity is a newly published dataset, a global dataset for river floods. It's called Caravans. This is not our dataset, but this allows us and other teams around the world to access and do analysis and modeling to help better handle flood predictions. This Caravan dataset includes meteorological forcings, for example, precipitation, temperature, catchment attributes, for example, elevation, slope, climatic indices, for example, which climate zone does the river is situated in, and hydrological signatures such as basin areas. So the urgency, together with the opportunity, brings us to a point where we can start actually produce things to help emergency agencies prepare better for such floods. And with that, I would like to pass to Joanna.
Thank you, Omer, for the powerful introduction. And now I will walk us through the problem definitions for our regional flood prediction model and the global flood prediction framework we have developed. So let's start with the motivation for a regional flood prediction model. The the main question we investigate is how can we use machine learning and caravans, the dataset that Omer just presented. How can we use machine learning and caravans, the dataset that Omer just showed, to predict, to better predict river flood events? And what do we mean by better predictions? We mean that we need to be able to predict river flood events as many days in advance as possible, and we also need more accurate predictions. So why do we need days ahead predictions? Let's take a look at what happens when an extreme flood event occurs. The disaster charter is activated onset of the flood event, and then it can take 12 to 48 hours to deploy emergency response teams worldwide. During this time, flood maps are generated using satellite data and are provided to the teams to facilitate mitigation. However, note that the satellite data is available in a coarser temporal resolution, making it difficult to render the development of the flood extent as it happens. For this reason, it would be really beneficial to have confident predictions in advance, telling us whether a river flood event will occur and how severe it could potentially be. These predictions would be crucial to first responders, who can be standby in high-risk areas and provided with more helpful information prior to their dispatchment. So what is our problem definition? Let's use a simple example here. Let's assume that my house is located in a basin and there is a river running nearby. And it's Friday afternoon currently, and we would like to know whether a flood event is possible during the weekend. So what do? We collect some data, some weather data, as well as catchment and hydrological information for this basin. And we collect this data, let's say, since the beginning of the week. So every day, Monday through Friday. And we predict for the weekend the following three. First, what is the daily mean stream flow? Second, do the stream flow values mean a flood event is about to occur? And three, in the case of a flood event, how severe is it going to be? Note also that uncertainty quantification is crucial in our problem definition, as the further ahead we try to predict, the more uncertain our predictions become due to the time series cumulative error. So we are currently working towards incorporating uncertainty quantification in our current results. So I already mentioned the need for accurate days ahead predictions. Now it would be really meaningful if we can also extend these regional model predictions to basins around the world, outside the regions that are currently documented in caravans. Caravans currently represents a limited number of regions around the world, even though US, Brazil, Australia are large countries that provide us with high variability of catchment and climatic profiles. So in the regional model that uses caravans, we have available some dynamic variables that mostly comprise of meteorological forcings and hydrological signatures. The remaining attributes are assumed to be temporally invariant and include catchment attributes and climatic indices. Therefore, to generalize predictions to a global scale, we propose a framework based on which we replace the historical meteorological forcings available in caravans with data available on a global scale. The dynamic attributes then include reanalysis weather data available from Era 5. Yes, so we basically replace the dynamic attributes available in caravans with reanalysis weather data that are available in Era 5, as well as hydrological signatures from the Global Runoff Data Center, the GRDC. And in addition, the static attributes are all available in the HydroAtlas dataset on a global level. One last thing worth noting here is that it would be really interesting to extend this current pipeline we have to use near real-time dynamic input in the future, as well as incorporating forecasted meteorological data from, for example, from NOAA. And now Manu is going to walk us through our machine learning pipeline. Thank you.
So thank you guys for walking us through the needs and challenges of a global flood prediction model. We are really excited to share with all of you Floodcast AI. Floodcast AI is a framework for training machine learning-based global flood prediction model. The models that are trained will be trained on the raw data that is collected from caravans, and then we do an evaluation split. We do holdout and stratified split. These splits ensure that our model are trained and evaluated and are generalizable to unseen gauges as well as unseen climates. Then we chunk our data into smaller portions. These smaller portions ensure that our pipeline can work on any computer. And then finally, we train our models. These models are trained to predict the streamflow values of the future. And then we have evaluation of our models. This pipeline is used to train the model in Floodcast AI. Using this, we train 4 different models. We have a baseline linear regression, we have a baseline random forest, and on top of this, we have a deep Markov chain neural network. This deep Markov chain neural network predicts the mean and variance of the streamflow values. This helps in quantification of uncertainty that Yuna was talking about. Then we finally propose a 2-path LSTM. This 2-path LSTM keeps the static variables and dynamic variables separately and uses a decoder encoder and LSTM model for the time series values and a simple neural network for the static values. Using these 4 models, we make the predictions for streamflow for 3 days ahead. And these are the results for the 2-path LSTM. For 0 day ahead, for today, for Friday, we are perfect. We estimate the peaks accurately. The blue lines are the observed values and the orange lines are the predicted values. Then we get similar results in 1 day ahead and 2 day ahead as well. For 3 day ahead, our models are accurately able to estimate when the streamflow is going to peak. These peaks represent the floods. These floods can be estimated 3 days ahead and a disaster response can be activated. And then finally, we compare our models. This comparison results, we see that the 2-path LSTM outperform all the models that we have. In the left-hand side, we have the RMSE values for all the models, and these are less than 2 millimeter per day, which is very less. Then on the right-hand side, we have the recall values. These mean that out of the true floods, how many are correctly identified. The models that we have trained in Floodcast AI are able to predict approximately 50% of the flood 3 days ahead. Based on these analyses, we see that Floodcast AI has a huge potential for making a global flood prediction model. And now I would like to hand over to Kiki.
Thank you guys for the great presentation. Well, you saw the evaluation that we did in our caravans test set with the holdout and stratified splits, but we also wanted to evaluate the spatial generalizability of our models in unseen gauges, in gauges outside the caravans dataset, and in the locations where we would like to actually predict well. And for that, we extended the caravans dataset with 195 locations selected across Africa and Asia. And for those, we collected the streamflow data and also the inputs that our models use. And we ran the Markov chain neural network model. And for the whole dataset, we get an error, a root mean square error, or 3.62 millimeters per day, which is a bit higher than the error that we get in the caravans test set, but it's still really good, considering that all these points are really far from all the training samples that our models have seen. And also, if you look at this 3 day ahead prediction, you can see that the predicted streamflow actually is really, really accurate. So we can claim that our models are generalizing well to these unseen gauges in outside caravan. So now you saw our predictive results, but how does this translate into the real world? So who benefits from it and how? And what you are seeing here is a simulation generated by NVIDIA Omniverse from a flood event occurred in South Africa recently, like this year. And you see that the idea is that the precipitation was falling into this basin. And and the river levels increased, making the banks overflow, and the water went into the floodplain where there are these human settlements causing damage. So what we can do now with our model is, and this is work in progress, is to use the outputs of our models to generate realistic simulations. You can see here how the river flow is going back to normal. We can use the outputs of our models to generate realistic flood extent simulations, and use that to warn the local authorities and emergency response in charge of that area to have better mitigation and response of the events. And lastly, to summarize our project contributions, here we're presenting the first benchmark of caravans for global applications and concretely for river flood prediction. We are presenting Floodcast AI, which is a pipeline and models to predict if a river is going to flood in the next 3 days, and also the magnitude of this flood. And because we have used global available data, and also we have carefully checked that our models are spatially generalizable, we can use these models to predict anywhere in the world, and we have shown that by predicting in locations in Africa and Asia. And lastly, because we have tackled these two, which are key requirements of emergency response, which are the 3 days ahead prediction and also the spatial generalizability, we can now work on deploying our models in an operational framework that actually helps to improve the current response against flood events. And we are really, really excited about this. And as a closing remarks, we would like to thank everyone that contributed to make these results possible. And also say that the framework will be openly available. So we would like to invite everyone to collaborate with us. And we are really excited to see what the future will bring for Floodcast AI. And thank you everyone for watching.
Thank you so much, Kike and the hydrological team. That was an amazing presentation. Just while the aerosols team are setting up, I'd like to go over and talk to some of our faculty. So I'd like to welcome Paula Harder, Dietmar Backes, and Cara Lam, who have been working on FDL for a number of years now, and who are faculty, that is mentors and team leads for some of our teams. Welcome. So you're all veterans of FDL now. How do you think the teams are feeling at this point in their journey? And I know the showcase is where they present the results, but often there's a lot more work to be done in order to get to the final paper and the final system. Who would like to take that first? Maybe Paula.
Yeah. So yeah, thanks for that question. As I've been there myself before, I think this is a very exciting point of FDL. So I think the researchers feeling, it's like a mixture of excited, proud, and a little tired, because those 8 weeks been very hard work. So it's a moment to look back and feel great about what they achieved, but also afterwards to wrap things up, start a publication, polish the code. But I think we have a lot of reason to be proud. The researchers.
Absolutely, yeah. Cara, you've been getting up very early in the US to support the European teams. Do you think it's all been worth it?
Sorry, do you mind repeating that?
Oh, no, I'm just saying you have been getting up very early and putting in long hours to support the teams from the US to Europe. How do you feel? Has it all been worth the hard work?
Yeah, it's been great. I think especially the last 2 weeks to just see all of the hard work the team has been putting in pay off as they get their machine learning pipeline finished, or there, and have all of these results coming out that they're going to be showing next. So that's been super exciting to see, is just seeing everything come together now at the end, and seeing that just how much progress the team has been able to make over the past 8 weeks, because it was just really quite a bit of work for everyone on the team, but they all contributed a huge amount over these past 8 weeks. So that's been really exciting to see.
Yeah, great. And just to point out as well, I mean, I know that you've been involved for a lot more than 8 weeks. in the sense that, we've started spinning up this at the start of the year, and it's really a year-long cycle. So the team won't go put their research to bed, if ever, until September or after. Dietmar, just before we go over to the aerosols team, what is some advice that you might have to offer for the teams as they go forward after this showcase?
Okay, we've done it once. So at this point in time, it's certainly great to be proud and look back on the last 8 weeks. But what people actually realize, we just started the action, and what's coming can be rather great building into operational system and, of course, great publications. Being injected in the scheme a little bit late, so I didn't have that much preparation time and that much involvement as, for example, Kara did. I was always admired her for getting up at 3 o'clock in the morning to be around. But all the three of us have been through the researcher stage and have seen projects executed in the end and published, and to the case that published result has been achieved. And here, I think, is the advice to the teams that this will be an interesting journey which continues far later than this August or September. So we are looking forward to meet the guys in September in Oxford.
Fantastic. Thank you all. And now it is my great pleasure again to introduce our aerosols team.
Climate change is driving an increase in frequency and intensity of wildfires all around the world. The fires in Australia during 2019 and 2020 burnt more area than in any fire season in living memory. Since then, fires have continued to rage around the world, in the United States and most recently in Europe, in response to extreme temperatures. Anecdotally, we're seeing more fire-generated thunderstorms, pyrocumulonimbus, with powerful convective updrafts that increase the intensity of the fires and carry burning firebrands for many kilometers. They may also have important climatic effects, since collectively they add huge amounts of aerosol to the upper atmosphere. We need to know more about how and why cumulonimbus form, and their effect on the climate. Machine learning offers the possibility of detecting all examples of these pyrocumulonimbus using satellite data, and unraveling the causes and effects.
It's an honor for us to present to you our project, which we've been doing for the past 8 weeks, where we try to address the question, what if we could understand and respond much more effectively to wildfires than we can now? So on our team, we have me, so I'm Ashwin Browder. I'm a researcher in remote sensing of planetary atmospheres. We also have Kenza Tazi, who's a PhD student in artificial intelligence applied to environmental risk. We have Emiliano Diaz, who's a researcher in causal inference methods in machine learning. And finally, we have Daniel Oko, who's a researcher in space weather. And we're also very indebted to our faculty and our research advisors for facilitating this project and guiding us all the way. So, of course, it goes without saying that wildfires are extremely destructive. They destroy communities, they destroy ecosystems, they lead to property damage, and more importantly, they cost lives. And so what we have here is a picture of a particularly bad wildfire in Northern California that started around 2 weeks ago, and it's already burnt an area the size of Birmingham, and it's been very, very difficult to contain. And part of the reason why it's been so difficult to contain is because it's been producing these storm clouds that exacerbated the fire even further. So how do these large and intense wildfires cause these kinds of storm clouds in the first place? So the principle is that if a fire is large and intense enough, you'll create so much smoke, which will ascend so high into the atmosphere that the smoke will condense and form clouds. And under certain meteorological conditions, these clouds will form thunderstorm clouds. So these thunderstorm clouds are known as pyrocumulonimbus, or pyro-CB for short. And these pyro-CBs are extremely dangerous for two main reasons. First of all, they cause lightning, which can ignite further wildfires. And secondly, the This fire causes unpredictable weather patterns. So it causes turbulent winds, which can fan the flames of the fire even further. And it can also cause the fire to change direction very suddenly and in unpredictable ways. And this poses an enormous challenge for disaster response teams. So only a very small minority of wildfires actually result in pyrocy, because you need a particularly large and extreme wildfire to do this. But what we're seeing is with climate change that we're predicting a 50% increase in the number of wildfires up to 2100 from here. And what we're seeing is wildfires are also set to become more intense. So the number of intense wildfires that are actually going to lead to these pyro-CB events is going to go up in even more than this. So it's becoming much more urgent and imperative to be able to better understand pyro-CBs. So essentially what we need is a good strategic containment strategy. So what we need to be able to do is identify the wildfires where pyro-CBs are likely to take place and try to contain those fires as much as possible so that they don't produce a pyro-CB. But we also have to plan and anticipate for the fact that perhaps the containment will fail. So so we have to plan for evacuating many more people. And if we can do this as early as possible, we can have a much better strategy. And so if in case the pyro-CB causes the wildfire to move in unpredictable ways. But of course, to be able to do this, we need to actually be able to identify which of these wildfires are most likely to produce pyro-CBs in the first place in order to be able to allocate finite resources towards those particular fires. So essentially what we need to be able to have is a machine learning model that can first help us better understand the interplay between the properties of the fire and the meteorological variables that are most likely to cause a pyro-CB, and hence allow us to better predict when a pyro-CB is likely to occur simply by looking at a geostationary satellite image of a wildfire earlier in the day. So the question we have is, are we able to produce some sort of prediction model that can forecast a pyro-CB given a wildfire earlier in the day? And that's where I hand over to Emiliano, who's going to talk more about the obstacles that we face in doing so. Thank you.
Thanks, Ashwin. So why now? Why hasn't this been tackled by AI before? So the information that we will use at the spatial and temporal resolution that we needed has been around since 2018. And why hasn't it been this tackled before? So it's three interrelated problems. There's we don't know where to look. So that's related to labels. There's a large amount of information that's related to the temporal resolution, which we need the information. And there's also the amount of wildfires that are out there. And there's also the way that the information is organized. So could break down a little bit these challenges. So here on the left, we have an image from the Himawari geostationary satellite, which orbits at the same rate that the Earth spins. So it's always looking at one place. And we see that it covers East Asia and Australasia. And on the right, we have the Australian subcontinent, and we have mapped on there the frequency of wildfires during 2019, with blue being a little bit less frequent, and then up until the cyan, which is more frequent wildfires. And so what we see is that there's a very, very large amount of wildfires, and we need some prior detective work in the form of labels to be able to narrow down which wildfires are potentially produced pyro-CB, and then go look at those images and see if we can spot conditions that led to the pyro-CB. And regarding the amount of information that there's out there, as we mentioned, we need high temporal resolution. These satellites provide that. They provide 10-minute frequency of observations. On the left, as before, the Himawari. On the right, we have the GOES satellite, which looks at over the Americas. However, if we have the detective work, we would be able to just download the little square, the little red square, which represents our label. However, because of the way that the information is organized, we actually need to download the whole of the image disk and then crop out the area that we're interested in. So that was one of the big challenges. So basically a download bottleneck where we had to develop the tools to be able to download these large amounts of information. So Ashwin talked a little bit about the need for a 6-hour ahead prediction model to aid containment and evacuation efforts. And I talked about the challenges, and the challenges refer more to the database, to be able to develop the database so that we can go on to the forecasting. So we identified these 3 components that we need: the database, which includes data, images, weather, labels, and download tools, the forecasting model, and also a discovery framework within which we can try and interpret results from the forecasting model and sort of feedback on the modeling efforts, but with a more robust sort of causal understanding of PyroCBs. So this is why we're very proud to present to you Pyrocast. It integrates these 3 components. It's an end-to-end machine learning pipeline that aids in analysis and forecasting of PyroCBs. And I'm going to pass on to Kenza, who's going to talk about the first 2 components, the database and the forecasting model. Take it away, Kenza.
Thank you, Emiliano. So to create our database, we start by curating historical PyroCB dates and locations from blogs and sparse online databases. And then we match these with global wildfire records from the GlobFire database. The next step is to find the satellite image data. Most PyroCB events are located in North America and Australia, and we also need to get a good temporal resolution to study the evolution of the wildfires, as Emiliano mentioned before. We therefore choose Himawari 8 and the GOES 16 and 17 satellites to download the data from. We choose 6 bands or wavelength channels that should, according to the literature, give us the best chance at predicting and detecting PyroCB. You can see these on the right now. As Emiliano explained earlier, we need to sieve through a lot of data, so we spend a lot of time creating an efficient parallelization pipeline using Apache Beam and data flow software packages. Thirdly, we use a pre-existing PyroCB detection algorithm developed at the Naval Research Laboratory, or NRL, to label our images. Again, you can see the output on the right, which shows the formation of a PyroCB cloud. Finally, we match meteorological and fuel data from a climate reanalysis model called ERA5. And so here are some examples from the outputs for relative humidity at the top here for 650 and 850 hectopascals, the wind at 10 meters and 250 hectopascals, and then also the available convective potential energy, or CAPE, and the surface latent heat flux. Altogether, these components give us our PyroCB database. To the best of our knowledge, Pyrocast is actually the first comprehensive database of PyroCB events. It is made up of 148 PyroCB events that are linked to 111 wildfires between 2018 and 2022. This represents over 40,000 hourly observations of wildfires in 6 wavelength channels and also 19 meteorological and fuel variables. Excuse me. Yes, so most importantly, this database is science and machine learning ready. This means that for the first time we can study these events in a systematic way, but also make inferences about the characteristics and the causes of PyroCB. So now I'm going to talk to you about the Pyrocast forecasting model. We use a convolutional neural network to predict whether wildfires will generate PyroCBs 6 hours ahead. The network is relatively shallow as to not overfit on the limited number of events that we have. We combine 6 wavelength channels and our meteorological and fuel variables as inputs, with the flags generated by the PyroCB detection algorithm as targets. The model outputs a binary classification using cross-entropy as a loss function. So using 17,000 observations with an 80-20 train test split, our best model is able to predict PyroCBs with an accuracy of 93%. This could give emergency responders enough time to evacuate safely from dangerous wildfires. On the right, we have a receiver operator curve for our best model. It plots the true positive rate as a function of the false positive rate. The dashed line shows the performance of a random classifier, and the model performance is shown with the continuous line. This graph shows that even when the threshold for predicting PyroCBs is very low, i.e. a low false positive rate, the model can confidently predict which wildfires will generate these events. The orange marker shows the true positive rate and false positive rate for a quoted accuracy. So now I'm going to pass on to Daniel, who will tell you more about the discovery framework.
Okay, thank you, Kenza. Yes, so for our Pyrocast discovery framework, we are interested here to using our machine learning pipeline to understand which parameters, meteorological, that could impact or are most important for the prediction of PyroCB or that make PyroCBs to happen. And what we see on the screen is a random forest classifier analysis where we run the test on our 19 meteorological parameters, and we came out with these 6 as the most important parameters for affecting or influencing occurrence of PyroCBs. So we see that the boundary layer height here at the bottom and the CAPE, which is a convective available potential energy, are the most important parameters for occurrence of or predicting the occurrence of PyroCBs. And so we also pushed our machine learning pipeline further by, rather than just predicting the occurrence of PyroCBs in 6 hours time, like Kenza explained, we are interested to also use the pipeline to study or investigate which connections between the parameters are more important for prediction of PyroCBs. And yeah, what the architecture we use is just a simple or a modification of our architecture, the one Kenza talked about. But here we rather split into pathways, as we can see. And in one of the pathways, we introduce environment variables. The reason is that we expect that non-causal variables will need to be mixed with these environment variables to become predictive. And on the other pathway, we use the causal we expect the causal variables which are not mixed with environment variables because they will be robust to predicting PyroCBs. So, and on the next slide, on this slide, we are looking at the results from that machine learning activity. So we see basically these five parameters is important, and then the links between them are more important. So for example, we are seeing that there is an important link between the relative humidity at 3,500 meters and the CAPE, and also a link between the CAPE and the haze, and so on. So we find these links are the important ones, but most important link of all ones is this one we indicated in the bold line, which is the link between the CAPE and the 0.86 micron. These microns are the different channels or wavelengths of our geostationary images. And yeah, why or as an explanation or what could be responsible for this strong link is the expectation that the CAPE, which is a measure of instability in the atmosphere around the fire, is important because it tells how much how easy the smoke or plumes could be moved into the atmosphere upwards. And also the 0.86 micron actually presents information about the vegetation, which acts as fuel for the wildfire and PyroCB activity. So we found the 2 most important. And then, yes, so in summary of our contributions, we have developed the first comprehensive PyroCB database, which will enhance further studies of PyroCBs. And we have also developed the first PyroCB forecasting system in 6 hour ahead time. And additionally, we have used our machine learning pipeline to provide better understanding scientifically of the properties and causes of PyroCBs. So here we present to you the Pyrocast. We are super excited to present this to the society, and we expect that this will be a good channel to save lives and evacuate people and improve resource allocation, especially during the occurrence of pyro-CB. So thank you for listening.
Thank you very much, Aerosol's team. That was a fantastic presentation. So now we're going to have a panel who will comment on the results and give us their thoughts for the future. I am delighted to welcome Pierre-Philippe Mathieu, who's the head of the ESA Explore Office, Alison Lowndes, who is Senior Scientist of Global AI at NVIDIA, Martina Butter, who is a Natural Catastrophe Specialist at Swiss Re, Rochelle Snyder dos Santos, Earth Observation Scientist at ESA, Zahan Barmal, Senior Director of Strategy at Google, Frederick Katzert, who is a visiting research scholar at Google also and an expert on hydrology, and Michael Obensteiner, who is Director of the Environmental Change Institute at the University of Oxford. Welcome and thank you for joining us.
Thank you.
So I'd like to start off maybe with Pierre-Philippe. Why do you think the new results and capabilities are important, and how will they address our needs?
Okay, first of all, I want to congratulate the team. I have witnessed really an evolution in the quality here since the beginning, and it was a really impressive presentation, I must say. Extremely good material, a very good narrative, and high-level content. So the famous expectations, I think, have been met. And I understand there is a lot of work and sweat and long night behind this. So again, congratulations. What I also notice is that the two use cases are touching on two things which are increasingly important for us. First one is simulation and prediction. And we have seen how the machine learning can fuse different data in order to project this into the future with some level of accuracy. That sometimes beats a state-of-the-art model because they are much more robust and they keep learning. And the other one is more physics-based and understanding of processes with a relationship between variables, which becomes increasingly important for the uptake of this technology by the scientific community. They really want to understand the black box and understand, let's say, how things are related together by physical principle. So I really like the two approaches here. One is very applicative for society, and the other one is more sciencey. And I think these results can be used. And if you look, for example, at the flood, what really resonates to me is that in the previous edition of FDL, you've been looking at the monitoring of flood and in particular the impact after the flood. Here you predict things so that you can anticipate. And in our strategy to put this on board and to react extremely fast to disasters and possibly anticipate this, this is a natural next step also for me. Imagine the satellite that can predict probability of risk and then automatically steer to some regions of interest. So I'm really pleased, and again, congratulations.
Fantastic. Thank you very, very much. Martina, what are your thoughts?
Can you hear me now?
We can hear you now, yeah. Fantastic.
Okay, sorry. So thank you very much for the invitation and for the very insightful presentation. You can clearly see there's a lot of work behind them. Thanks. Maybe a brief introduction for who is not familiar with the insurance world, the natural catastrophe in insurance world. I work as flood specialist, and I was very happy to learn about the application in flood predictions, very interesting for us. And in my role, I basically contribute to building and improving the flood modeling framework and to build a view of flood risk. So basically, in a nutshell, with our modeling framework, we basically overlap an hazard module, so flood prediction, with an exposure module, meaning potential exposure which can be hit from a flood in an area. And the goal is basically estimating a potential loss due to a flood. And we want to explore a spectrum of possible flood events, from the smallest ones and more frequent ones to the really catastrophic ones. So looking at the current natural catastrophe modeling landscape, I see this machine learning approach very innovative, because so far more traditional, maybe more physically based models have been used. So I really appreciate this, because I think flood is a very challenging peril to be modeled, because of its very local nature, and it requires really a lot of data for the modeling. So I think exploring new modeling approaches is very valuable at the moment. And it's very interesting for us, the fact that it aims at a global coverage, because ideally we would like to have to be able to model flood hazard globally with like a very homogeneous standard, but this is not possible. And as it was highlighted during the presentation, unfortunately, floods happen all around the world and very frequently. So that's highly appreciated. Of course, we're interested in this forecasting mode, although we work on different time scales, but the approach is very interesting for us. And another interesting point is the application to the flood mitigation and prevention, because this has a very good feedback on the insurance industry, because more mitigation and prevention means also adaptation, and so lower risk, which can hit also the insurance business. So these are, from my point of view, are the main valuable points.
Fantastic, thank you. Does anyone have any responses or replies to make to Martina? Okay, Frederick, what were your main thoughts coming from the perspective of a flood modeler?
Yeah, thanks. So maybe for a little bit of context, I'm working at Google at the flood forecasting team that Zahan mentioned in his introduction. And I'm also the author of the caravan dataset that has been used in the study. So I'm very pleased to see, actually, I think it's probably the first application of this dataset, which is very new. And I think it's very exciting to see people make use of new datasets, open datasets. So my day-to-day work is quite similar to what has done here. So I can first off congratulate the team. I know it's a lot of work what they have done in the last weeks. I know it's quite challenging, and but I think there's a huge opportunity currently in this area, as the gap between what we currently have available as operational flood forecasting models and what can be done with the research results from like the previous years is quite huge. And a lot of exciting research is currently happening, and the team here definitely touched on this. So my thoughts are that, yeah, the team did amazing work. I think what we really need and what is missing is that we are missing globally observations for the areas that are most affected by floods. We have a lot of observations to train our models in areas of the world that are already covered by local models specialized to, for example, North America or Europe. But areas that are most affected by floods, like third world countries, developing countries, usually are quite sparse with observation data. And it is true, what the team also presented here, that we have ways to train models and apply them to different gauges. Still, we have seen from our day-to-day work that definitely it still helps to have data, at least from the region or from close by. And I think as like the whole community working in the field of flood prediction, we should work together towards trying to get a more open data, more shareable data, to collectively like make flood predictions better in the future.
That's great. Yeah, I know that data is a big issue in fires also, and it was a major issue for the aerosols team. Has anyone got any comments on the usability and future-looking possibilities for the Pyro CB work also? Maybe Michael, would you have some thoughts there?
Yeah, well, for Pyro CB, well, first of all, again, I need to join the chorus of the others on congratulating the team to accomplish so much in little time. This is, as I understood, it's a 6-hour forecasting system. And what's interesting about it is how can we integrate this in operational systems that I actually, currently I'm sitting here in France. France is hit by wildfires at the moment, and how can the operational systems really benefit from this? And there I have 2 comments. One is more technically. I think my understanding of the analysis is that it actually took instantaneous variables for the CNN analysis, and it would be interesting to look into lagged variables and cumulative variables to probably increase the predictive skill. The predictive skill is already very good, but false positives is also relatively high, and to my taste, a little bit too high. So some additional work on the predictive skill would really be good. And then see and share this information with these operational guys who, run observation stations on detecting fires instantaneously and so forth, and work a little bit on the larger system and integration of early warning systems, and then operational deployment issues for getting airplanes from other regions. Now I'm just sticking to the European example again, where we have a system where other countries are helping other countries. And if you have 6 hours lead time, you can actually fly a plane from, from Austria to France to actually help. And in this case, for these very operational decisions, 6-hour lead time on a Pyro CB is really valuable information. So my recommendation is let's hook up to the operational guys and see what the opportunities for actual implementation is. Over.
Great, thank you, Michael. Rochelle, what are your thoughts?
Well, that was a great presentation. Thanks first for inviting me to join this showcase, which I hear with great interest because I work a lot with public health applications, air pollution, and high temperatures. So this was very applied to my area of research. Just to those that don't know about me, just a brief as well. I work at ESA together with Pierre-Philippe Mathieu in the PhilLab and in the AI applications for the Destination Earth initiative. Those that never heard about that is the young brother of Copernicus program. So this idea is to build digital twins in a higher spatial temporal resolution. So exactly the topic that we are talking today, so which is great. So I can provide a lot of great feedbacks on that. So these activities today is very aligned with the Destiny goals in developing these models to benefit society and help us to increase the knowledge before an event, flooding event happens. So first of all, I just thank you all the teams for these important topics in a very short time, like 8 weeks of very hard work. So congratulations to all. And I can highlight these activities are not just important for science, as we saw for the technical abilities in using artificial intelligence, using Earth observation in a wide range, but also, as I mentioned, for societal impact, for importance this to public health. And as we know, flooding affect negatively as the wildfires to the population. And then this is important for us to create alert systems that allows us to to make this less impactful for our population worldwide. So in terms of feedback, actually from the projects, I was very happy to see the diversity that the teams used data. So I saw Earth observation satellites, I saw modeled and simulated data, for example, the ERA-5 that was mentioned, observations directly measured by other systems, and also the diversity of your machine learning applications. So as we know, it's a very complex tasks to be able to forecast flooding systems. So sometimes one machine learning algorithm we're not able to do from X to Y and solve all the problems. So I saw that the teams have used two-stage machine learning approaches. So have used one machine learning application for one step, and then once this is solved, use machine learning for another one. I think this is a great idea, and then helps us to deal with complexity, and as you mentioned as well, uncertainty around that. So, and one topic that, one thing interesting as well is the use of some other, let's say, technologies to bring this information at the end. So you solve, let's say you start doing data collection, machine learning applications, but in the end, how to communicate the results of that with people that are non-experts in machine learning. So your visuals, your simulations showing, for example, the flooding, was great, because these actually we can communicate with people that are not expert. What is the result of all these AI modeling and using Earth observation for that? I think this was a great communication strategy for that as well, and it should be used perhaps in the next showcases as an addition to how to use other technologies to implement the visualization of the projects. And I think I will stop here. Thank you.
Great, thank you. I know Alison is online too, but she hasn't been spotlighted because her video is not working. Alison, what are your thoughts?
Well, first of all, well done to everybody. Obviously, we're still in not brilliant times for working together as teams, but we have the virtual technology, so we're excellent. But both of these topics are so relevant. I mean, as Michael said, understanding the apocalyptic pyro CB will help everybody. I mean, even now, the UK's fire service are crying out, saying that we're ill prepared for this tinderbox situation, you know, right across Europe, across at least southern and, you know, Middle Earth, as we call it in the UK. They can put fires out, of course they can, but without, you know, let's say significant increase in resources, you know, society as a whole just is not ready for this unprecedented scale of risk from tinderbox situations, especially when the water you need, you know, this is the ironic thing, we're talking about floods in one place and fires in another where we have limited water to even put them out. You know, that's the state of the world. So we really have to get to grips with this. Deployment is always my focus. You know, that's what NVIDIA does, as well as the research, etc. And my personal view is that the tried and trusted models like LSTM can be put into orbit, but we really need to be using state-of-the-art here on the ground. You know, we need the kind of 100,000x speed up on the inference side that comes from using tech and you know, algorithms like for neural operators, for example. We have to bring all of this together. So I really, really want to see both teams' work implemented, you know, deployed to start helping in not only the prediction side, but the planning and the management. And, you know, we have to start deploying now. You know, we're literally on fire now, you know, or other people are, you know, while other people are flooding. So brilliant, brilliant work. You know, I am applauding. I know you can't see me. I can't figure out this camera. That's the state of the world. But yeah, wonderful. Thanks very much to everyone.
Thanks, Alison. And I think we all take your point about using the best models and the best algorithms that we can. But there's another point as well, to make sure that they're fed with the right data that doesn't have biases and is understood really well for confounding variables also. So we're almost out of time, but I'll just go over to Zahan for your thoughts also before we wrap up.
Thanks. I mean, again, I would just echo what my other panelists have said. Hugely inspiring work. Big congratulations to the teams involved. 3 reasons why I feel optimistic after this discussion. 1, I think this work shows again the power of AI tools when democratized to 10x science. Number 2, these presentations show the potential of technology to explore uncharted territories, to be implied in new environments, solving real critical problems. And 3rd reason, I feel optimistic. It's great to see this multidisciplinary work take place between domain experts and AI experts collaborating towards a common objective. So those are my final 3 thoughts, and congratulations again.
Fantastic. And thank you very much to our panel. It's been really interesting hearing your thoughts. I'd love to be able to talk more and follow up with more questions, but unfortunately we're almost out of time. So I'd like to welcome back the teams and the faculty as well. This is the part of the showcase where we do our innovation awards. So let me just go over to that. Usually we run an award every year for 2 seconds. Usually we run an award every year for unexpected discovery. And today that award goes to the entire of Hydro team for exactly the reasons that were mentioned by our panel here, for the use of novel machine learning in order to solve quite a tricky problem. We also want to award the entire aerosols team for keeping up high spirits during extremely challenging times. They had a lot of data engineering to do in order to sample their very sparse events in a very around the world over a long period of time. And there's a lot of plumbing and a lot of work that went into their project in order just to get to the machine learning, and then they went above and beyond to go on to the machine learning itself. And I always think that a good data set is equally a good outcome. Finally, we have a couple of individual awards for steely-eyed operators. So this is, the first is to Ioana for always being positive. She was the heart and soul of our team, and was really someone who shined as having FDL spirit. And finally, I'd like to say well done to Cara Lamb for 8 weeks of early rising in support of all of the teams. So that's wonderful to see you all there. Thanks very much to all of the teams for your efforts. It was a pleasure to work with you over the last 8 weeks and indeed beyond. I'd like now to hand over to James Parr, who's going to talk to us a little bit about an event that we're holding in March, and which we'd like all of you to join and be part of. James.
Thank you, Cormac. And I just wanted to again say to the teams and researchers and faculty, just thank you so much. Like we're so thrilled with what you've done, and I'm still can't quite believe it really, in terms of where we were and now the opportunities that get unlocked by all your efforts. And so thank you really from the bottom of our hearts for that. I wanted to actually, Cormac, if you don't mind, just go back a couple of slides and just talk about sort of FDL and how FDL thinks about machine learning, just for the audience. What you've just seen is work in progress, and we use the ML-TRL, which stands for Technology Readiness Level, to describe the maturity of machine learning pipelines. And so FDL gets us about halfway. So on a scale of 0 to 10, with 10 being, your machine learning tool which you're using in the world, what you've seen is about halfway. And this is essentially a proof of concept. And of course, this is absolutely ready for publication in scientific journals. And that's where FDL gets us. The engineering that then precedes that takes us to TRL 5, 6, and 7, and that happens by the community. We often say that an AI isn't just for Christmas. Machine learning has to be maintained, and we do that using our SpaceML facility. And if you go to the next page, Cormac, we're big advocates of open science. We really believe that this work is for all humankind, and so therefore it needs to be shared. And if you are interested in building on the work of previous years, but also this year, we make sure that there are data snippets and beautifully annotated notebooks and all the tools you need to reproduce the work to make it ready and usable. So on the spaceml.org, you'll see, as I mentioned, digests of the work, notebooks that allow you to run a rapid experiment. And thanks to our friends at Google, there's usually about a $500 free credits that allows you at least to get your sort of arms into the project and understand what's going on. And then, of course, MLOps, which is the engineering tools that we develop as we go along. And we're sort of slowly building out a nice toolbox of tools for others to sort of reproduce the work as we go. So we're absolutely in the business of science, but we're also in the business of making tools that can be shared for everybody to reproduce what we do. So as with that as a sort of preamble, you'll have seen that we're kind of learning, and we're really sort of trying to get our arms around this opportunity of what Earth observation data can do when it's paired with AI. And last year, if you go to the next slide, Cormac, there was a call to arms, so to speak, from the World Economic Forum. And they said that the time has come to build a new type of decision support facility, an Earth Operations Center that leverages space data and expertise to conduct multidisciplinary science and engineering research to successfully manage and coordinate net zero efforts, which of course is very much the things that we've been trying to do with our friends at FELAB. And so we sort of figured, well, the World Economic Forum sort of called for this. Well, perhaps we have a little bit of the answer, not all of it, but a little bit. We've certainly had our toe in the water. And so what we'd like to do is essentially respond to this call. And so in answer to that, we're going to run a big international forum to really explore the engineering questions and that would be required to really build an Earth Operations Center, the sort of mission control for Earth that's sort of been discussed at the sort of higher levels. But we believe that actually to do this means diving in deep to the engineering. This is where the interesting questions are. And so with our colleagues at ESA and Oxford, we're going to do this next March, but it's going to start sort of in September. So all the discussions are going to form this, inform this big discussion. We want to dive in deep with experts like the people who are on this live stream today. This is an open invitation to please help us with this vision. And our aspiration really is to really start to understand at a really substantive level what's going to be required to build this this tool, which of course everybody can benefit from. Cormac started the live stream today by talking about this observation that, if we can't measure it, it isn't done. And this is the sort of moment we're in, this sort of crisis where we still use money as our best way of measuring the way that we decide to do things at the expense of natural capital. And the ability to use satellite data and AI is really the best opportunity that certainly we've seen to really sort of change that balance and say, well, actually, let's really understand the impact our decisions are making on the planet. Let's really start to understand the investments we need to make, but also not just put a finger in the air, actually understand those causal mechanisms as you've just seen from the teams presenting today. So that's the dream. It's an invitation to join us on it. We're really grateful for everybody who's sort of dug so deep this year. It's really a special achievement. So I just wanted to say thank you. Thanks to FeeLab. Thanks to Google Cloud, of course, Alice and the team at NVIDIA, Scan Computers, really this incredible kind of infrastructure that allows us get to the summit. So it is very much like climbing Mount Everest sometimes, you know, this infrastructure that allows us to do what we do. And of course, all of you for joining and being champions of us in the background, our friends and family, of course. So with that, thank you so much. Thanks Cormac and Anshul for leading us as ever. Thank you to the team behind the scenes, and we'll see you all hopefully again soon.